charged particles in planetary atmosphere. To embark on a mystical voyage into space physics, the topic that always keeps us on the edge of excitement. I invite ma'am to begin the wonderful session.
So, shall we start now?
Yes, ma'am.
Yeah. So, thank you, Sahil, for the introduction and a very warm good evening to all of you. So, first of all, I would like to thank the organizers for giving me this opportunity to interact with the young minds. So, being a space physics researcher, it's very heartwarming to see that QSAS has got a community of space enthusiasts. So I hope to see many names and faces from this group in future in the space physics research platforms. So keep exploring. So let us get into the presentation. So today I heard that today's audience is pretty diverse with folks from all sorts of background. So I have kept my presentation at a very fundamental level just to give you an overview of what space physics and aeronomy is all about. So my intention is to spark your interest so that you can dive into it later if you find it interesting. So I hope I will be able to open up some interesting ideas for you to explore further later. So let us get into the presentation. So I hope you all can see my presentation. Anybody there? Can you please confirm?
It is visible, ma'am.
Yeah.
Yes, ma'am. Yes, ma'am.
So let's start. So space physics is really getting a lot of attention nowadays. It has becoming quite a big deal in the world that we live in. So space physics is actually that interesting aspect of physics which tries to answer some of the oldest questions that we ever had. Like, what is our place in this universe? Or where do we come from? Or something like how all these heavenly bodies like the sun, the moon, and the planets are connected to us, or connected to the planet that we live in, that is Earth.
Atmosphere.
And so these questions have been asked for almost thousands of years, and I feel like it would be continued to be asked and answered for another thousands of years. So in a very broad sense, we can say that the space physics is the branch of physics that deals with the study of the naturally occurring plasma in our solar system. So I repeat, space physics is the study of naturally occurring plasma in the solar system. So when I say this, like you may ask, like, what is this naturally occurring plasma, or what is this plasma on the first hand? So we all have studied in our high school classes that matter exists in 4 states: solid, liquid, gas, and the 4th state is the plasma. So in the solid state, the atoms and molecules, or in general we say particles, the particles are subject to very strict discipline and they are in rigid order. So if you provide temperature to the system, or if you increase the energy to such a system, what happens? We comes to the liquid phase where the particles have more degree of freedom, but still they have constraints for their motion. If you further increase the temperature of the system, you end up in the gaseous state where the atoms and molecules are free to move. Now, if you keep on increasing the temperature of the system, what will happen? These electrons which are sitting within these atoms and molecules acquire sufficient energy so that they will be able to come out of these atoms and molecules and will be able to move on their own. They will have the freedom of motion. So once these electrons are removed from these atoms and molecules, they acquire a positive charge, and we say they are in an ionized state now, or the process of ionization has taken place. So now we have the positively charged ions and the negatively charged electrons which have the freedom to move on their own. And when charged particle moves, what happens? There occurs current. So in a very simple term, or in a very simple way, we can put it like plasma is actually a conducting gas. So that is, plasma contains positively and negatively charged particles which are free to move, because of which there occurs a current. So plasma is nothing but basically a conducting gas. So I said in the beginning that we in space physics we deal with naturally occurring plasma in the universe. So, or actually, not in the universe, I should say, it's in the solar system. SpaceX deals with the naturally occurring plasma in the solar system. So, where do we find this naturally occurring plasma in our solar system? Hmm? Actually, the largest amount of plasma that you can find in our solar system is at nowhere else but within our sun. The innermost region of the sun, which we call as the core of the sun, is at a temperature of the order of 15 million degrees Celsius. So imagine what a high temperature it is, 15 million degrees. So at such a high temperature, no particle will stay in the neutral state. The entire matter will get ionized and the complete material will get converted into the plasma state. So the sun is actually the largest holder of plasma in our solar system. We know this sun is not something which stands still, isn't it? Like it is rotating. Actually, every body in our solar system is rotating. So when sun rotates, what happens? This plasma within the sun also rotates. So again, the charged particles are moving. So when charged particle moves, current occurs. Again, in physics, in your +2 classes, you might have already studied. When the current flow occurs, there occurs a generation of magnetic field as well. So this motion of plasma particle generates a magnetic field. Now once this magnetic field is generated, it will have the capability of controlling the motion of the charged particles. So actually the plasma of the sun sets up a very complicated system in which the motion of the plasma is generating a magnetic field, and this magnetic field in turn is controlling the motion of this plasma. So this system we call as solar dynamo. Thus, sun actually consists of a plasma, a large chunk of plasma along with a very huge magnetic field. Now, another speciality is that this plasma and the magnetic field lines of the sun are not something which is constrained completely within the sun itself. So, like it is not something which always stays within or around the sun. So, I don't know how many of you have heard about the term solar wind. So I actually first heard about solar wind when I joined for my PhD. So then only I came to know about, okay, such a thing exists. So what this solar wind is? So this plasma within the sun is actually always sitting at very high temperatures. So that means they are always at very high energies. So as the energy builds up, at some point or the other, a fraction of these plasma particles of the sun attains enough energy to sun, it actually drags the magnetic field lines of the sun along with it. So in all those voids that exist in the solar system, like those between the planets or between the planets and satellites, or anywhere else, you can actually feel the presence of the sun's magnetic field. So at those places, that is at those locations outside the sun, we call this magnetic field as IMF, that is interplanetary magnetic field. So it is something like you have the plasma and magnetic field generated within the sun, and this plasma and magnetic field are not staying within the sun, but it is actually coming out of the sun and is spreading throughout the entire solar system. So now you can understand how plasma is spreading into our solar system. So how you might be getting a feel of why I said in the beginning, like most part of our solar system is actually filled up with plasma. Now, the solar wind is not the only sole mechanism through which the plasma from the sun can come out. So there is something called the CMEs, or coronal mass ejections. So coronal mass ejections are actually violent explosions that take place in the outermost layer of the sun called corona. So during this CMS, a large chunk of the plasma within the sun actually comes out. So that is what is shown in this figure. It comes out from the sun at tremendous speed and high energies and will be able to spread out through the entire solar system, impacting all the planets and satellites. So, I hope this particular slide has given you the feeling that sun is actually a large source and a distributor of plasma in our solar system. So in school classes, we always learn like sun is the source of heat and light. So when you get more advanced into space physics, you will come to know that sun not only provides heat and light, but it is also a distributor of plasma as well, plasma and charged particles as well. So like sun is actually a very important aspect of space physics. So if you want to dive deeper into space physics, so let me tell you, you just can't skip over the sun. So this is where the branch of space physics called heliophysics sits in. So heliophysics is that branch of space physics which explores the sun, its plasma, its magnetic field, and everything else that is affected by the plasma from the sun. Now, like you all might have recently learned about a particular mission called Aditya L1. So Aditya L1 was actually a mission which was sent by our country exclusively for studying sun and its plasma. So Aditya, the word Aditya, you all might be knowing, it's a Sanskrit word which basically means sun. So this spacecraft consists of a suite of instruments for studying the sun and its plasma environment. For example, there's a magnetometer which actually measures the strength of the sun's magnetic field. Then there is a spectrograph which measures the X-ray and UV emissions from the sun. Then what else? There's a plasma analyzer which is meant for understanding the solar wind and what is its composition, and many other instruments for understanding our sun. So that is why it is named as Aditya itself, because it is exclusively meant for studying the sun. Now you can see another term, L1 over here. So what is L1? Any idea? So L1 actually stands for Lagrangian point 1. So if you take any two-body system like the Earth-Sun system, like there will be 5 points within this two-body system as shown in this figure. So at these 5 points, if you put a third body, the force experienced by that third body from the gravitational pull of sun as well as the earth, and also the force experienced by the body due to the motion like the centripetal force, etc., will balance out each other. So at those particular 5 points, if you put a spacecraft, it will be able to stay at that point for a very long time with the minimal consumption of fuel. So if you so these spots are usually used as the parking spots of spacecrafts, so that when the earth moves around the sun, these 5 points will be moving along with the earth, so that we will be able to monitor the space without much interruptions. So here Aditya is put at the L1 Lagrangian point somewhere over here. So it is at a distance of about 1.5 million kilometers from Earth. So having a spacecraft over here allows for the continuous monitoring of sun without anything getting in between and interrupting the monitoring of sun. So that is what Aditya was all about. So Aditya is currently making observations of sun and its plasma environment, and we all are eagerly awaiting for the new science that Aditya is going to reveal in front of us regarding sun. So far I was talking only about sun, how its plasma is generated, how it is distributed within the sun and all that. So is it something like sun is the only place in our solar system where the plasma is generated? So like, can't we find any other source of plasma in the solar system? Actually, the answer is the plasma is there, or plasma is generated right within our atmosphere itself. Our atmosphere itself, plasma is getting generated. Within our atmosphere itself, the plasma is getting generated. So before getting into those details, I would like to discuss something about our atmosphere. So here I am showing the temperature profile of our Earth's atmosphere. So what is the temperature profile? So it basically tells you how the temperature of the Earth's atmosphere changes as you go up from the ground to the outer space. So as I have shown over here, the Earth's atmosphere is divided into different layers depending upon how the atmospheric temperature is behaving at each of these layers. The bottommost layer is the troposphere, where you have the temperature decreasing with increasing altitude. Above troposphere, you have the stratosphere, where the temperature shows the inverse behavior. That is, the temperature is increasing with increasing height. Then again, you have the mesosphere above stratosphere. There again, the temperature is reverting back to its previous behavior. That is, the temperature is decreasing with increasing height. So why the temperature is behaving in the way it is in each of these layers, I leave for you guys to explore. Now, above the height, above the mesosphere or above the altitude of 85 kilometer, that region of the atmosphere is generally referred to as the upper atmosphere. So again, upper atmosphere consists of layers like thermosphere, exosphere, etc. But in general, we refer to them all together as upper atmosphere. So a characteristic feature of this upper atmosphere is the very high air temperature that exists in this region. So you yourself can see over here how the temperature is rising, how it is reaching a very high value, and at high altitude it is staying constantly at a very high temperature. So why the air temperature is behaving in this particular manner at this high altitudes? So this occurs because of the thin nature of the atmosphere at these high altitudes. I don't know like how much you will understand if I say the thin nature of the atmosphere. Okay, I will try to put it in simple terms. Okay, near the ground, if you take 1 square centimeter area of the atmosphere, you are taking 1 square centimeter area, and you know, like atmosphere is nothing but just a mixture of gases. You get to see plenty of oxygen, nitrogen, carbon dioxide, argon, etc., etc. So the atmosphere is simply made up of the atoms and molecules of these gases. So suppose you take 1 square centimeter area of atmosphere near the ground, and suppose you are able to count the number of the gas particles within this 1 square centimeter area. So say like we counted the number of gas particles and let it be 1000 particles. So you got 1000 number of atoms and molecules within that one particular square centimeter area. Now if you take the same 1 centimeter square area at an altitude of about 30 kilometer, and again you count the number of gas particles within that square centimeter area, there you will be able to find only about 10 particles. So at the ground level, within a 1 square centimeter area, you got 1000 particles. Whereas if you go to 30 kilometer and take 1 square centimeter area and count the number of particles, there will be only 10 particles. So which means as you go to higher and higher altitudes, there will be fewer number of particles, or we say the atmospheric pressure is decreasing. So the pressure is nothing else but the force exerted together by all these particles. So as you go up to higher and higher altitudes, the atmospheric pressure is decreasing. So this is what I mean when I say the atmosphere is thinning as you go to higher altitudes. So at these very high altitudes, you have very fewer number of particles available in the atmosphere. Now when the solar radiation, the radiation from the sun is actually reaching us on the ground after passing through this atmosphere only. So when the radiation passes through this atmosphere, what happens? It heats the atmosphere, isn't it? But at these higher altitudes, there are a fewer number of atoms and molecules. So that means a large amount of energy from the solar radiation is distributed among this fewer number of particles, which in turn means that each of the particle will be getting a large amount of energy. So if there were more number of particles, the energy would be divided among this greater number of particles, so energy will be less. So, but here the thing is that you have a fewer number of particles and the energy is distributed among this fewer number of particles, because of which they all will be receiving a large amount of energy, in turn resulting in the very high temperature. So that is why you get to see high temperatures in the upper atmospheric region. Now it is within this upper atmosphere that you get to see plasma in the atmosphere. So now you might think like this plasma is forming in the upper atmosphere because of the large temperature which we discussed just now. But it is not so. So even though like in sun, the plasma was generated because of very high temperature, but here it is not that the case, because in sun we were talking about the temperatures of the order of millions of degree Kelvin. But here the temperature is only of the order of 1000 Kelvin or 1500 Kelvin, which is not high enough for causing ionization of the atoms or molecules. So here some other mechanism is causing the formation of plasma. So let us see what is it. So we all know solar radiation is reaching our atmosphere from sun. And again, this solar radiation consists of a range of wavelength starting from radio wave to gamma rays. Now in this electromagnetic spectrum, there are two wavelengths which are the ultraviolet and X-ray radiations, which are very high energy radiations. So when these high energy photons, UV and X-ray photons, interact with the atmospheric neutral gas particles, or when they collide with this atmospheric neutral gas particles, they transfer the energy to this neutral particles. So this will be a very high energy, which is sufficient enough to cause the ionization of this neutral gases. So that is what I have shown over here, that the UV and X-ray radiation are coming, interacting with the molecules or atoms in the atmosphere. So once the energy is transferred, what happens? One electron is knocked out of the particle, resulting in the formation of ion and free electrons. So this is how the charged particle or the plasma is getting generated in the atmosphere. So that region of the atmosphere where you get to see plasma is referred to as the ionosphere. So ionosphere is defined as the electrically conducting layer of the atmosphere, which consists of positively charged ions and negatively charged electrons. Now, just now I introduced to you like the temperature profile of the atmosphere, isn't it? So now similarly, like for making someone familiar with the ionosphere, ionospheric part, what we discuss is usually the electron density profile. So the electron density profile of the ionosphere is something like what I should say, like the ID card. It's like the ID card of the ionosphere. If someone comes and asks you who you are, the first thing that you will do is showing your ID card, isn't it? So in the same way, like to understand the ionosphere, the basic structure and dynamics of the ionosphere, we usually look into the electron density profile of the ionosphere. So electron density profile is nothing but simply something which tells you how the density of the electrons in the ionosphere is changing as you go to higher and higher altitudes. So here I have shown that this curve actually shows the electron density profile of the Earth's ionosphere. So the structure, as you can very clearly see from this figure, as you go to higher and higher altitudes, from around 100 kilometers, the electron density is slowly increasing. Then it maximizes at a particular altitude, and beyond that maximum height, again the electron density is decreasing. Now, why this structure is actually referred to as the Chapman structure of the ionosphere. Now let's see why this sort of a structure is coming to the electron density profile. So as I said before, like what are the two basic things which you need to form the ionosphere? One is the solar radiation, and the second one is the neutral gas particles to get ionized. So the solar radiation actually falls directly from the sun to the top of our atmosphere. So once it reaches the top of the atmosphere, it passes through the atmosphere and reaches the ground. So while it passes through the atmosphere, it gets absorbed. It gets absorbed by the atmosphere. That is, there occurs attenuation in the strength of the solar radiation. So the solar radiation will be having the maximum strength at the top of the atmosphere, and as you come to lower and lower heights, so you can follow this particular curve. So as you come to lower and lower height, what happens? The strength of the solar radiation, the UV and X-ray radiation, which are required for forming the ionosphere, is actually decreasing. Now, what's the second factor which is required for forming the ionosphere? It is the neutral particles. Now, just now we discussed how the neutral density is like decreasing as you go to higher altitudes. So, neutral density is maximum at the bottom of at the like bottommost layer, or at the region lying close to the ground. So, the neutral density is maximum close to the ground, and as you go to higher and higher heights, the neutral density is decreasing. So that means the solar radiation strength is decreasing as you approach the ground, whereas the neutral density is increasing as you approach the ground. So there will be an optimum height in the atmosphere where there is sufficient amount of solar radiation available to cause the ionization, and sufficient amount of neutral particles also available to get ionized. So at that particular point, you get the maximum ionization. So, and that particular layer, that is the region where you find the maximum plasma density in the ionosphere, is referred to as the ionospheric peak. So you can see this is the general structure of the ionospheric electron density profile. So at this point, that is where you have optimum radiation and optimum neutral density, you are having maximum ionization and hence the maximum plasma density. Now the question is, why we should be worried about this ionosphere? What bothers us? Like, if plasma is produced in the atmosphere, let it be there. Why we should be worried about it? So you I hope like this community includes students from electronics and communication background as well. So they might have already learned and discussed about the ionosphere while studying the radio communication systems. So when the radio signal passes through the atmosphere, the charged particles in the ionosphere bends this radio signal, sending it or reflecting it back to Earth. So again, it gets reflected back to the ionosphere, again reflected back to Earth by the like ionosphere, and the process goes on like that. So this allows for the long distance communication over the horizon. Then in another aspect, you might have heard about the ionospheres in the terms of satellite communication. So this ionosphere is capable of affecting the satellite signals. We all use GPS in our phone, right? So this when this GPS signals passes through the atmosphere, this ionosphere is able to affect this GPS signals and causing them to bend. So when this GPS signals bend, what happens is it will reach our phones at a later time than expected. So this will cause errors in reading the location. So actually, these GPS signals have undergone an ionospheric correction before coming into into our phones, so that we can have accurate locations. So these all are the aspects in which the ionosphere comes into picture in the day-to-day life. But as a space physics researcher, I would say the most interesting aspect of the ionosphere, which really makes it an interesting topic to work on, is that the ionosphere acts as the gateway of the Earth's atmosphere to the outer space. Excuse me, I will just drink some water and come back. Sorry for the interruption. Let us get back into the presentation. So as I was saying that the ionosphere is the gateway of the Earth's atmosphere to the outer space. So actually any change happens in the sun or in the outer space, you will get to see a signature of the same in our ionosphere. So actually the Earth has got a magnetic field. So the magnetic field generated by the Earth looks very similar to the magnetic field caused by a bar magnet. So this magnetic field of the Earth actually forms a cavity around our planet, and we call this cavity as the magnetosphere. So this magnetosphere and ionosphere plays a very crucial role in protecting our atmosphere from all those charged particles, all those energetic charged particles. I should say, like energetic charged particles coming from the sun. So, like if these charged particles comes in and directly impact our Earth's atmosphere, it can cause catastrophic effects actually. So when this solar wind or CME particles or whatever it is comes from the sun and reaches of the Earth atmosphere, a large part of it actually doesn't reach the Earth atmosphere. So before that itself, the magnetosphere deflects a large fraction of these energetic particles as indicated by this figure. But still a fraction of this energetic particle manages to get into the Earth's ionosphere. So once they get into the Earth's ionosphere, like they interact with these charged particles, and this ionosphere largely helps to dissipate the energy. So this ionosphere and magnetosphere acts something like sort of saviors for our Earth's atmosphere for protecting it from the space weather events. So okay, I didn't mention earlier what the space weather events are. So space weather events are nothing but just what we discussed so far. That is whatever eruptions that are happening from the sun, we refer to it as space weather events. That is the solar wind. I already explained to you what it is. Then so coronal mass ejections, that is also a space weather event. Then there is something called solar flares. So solar flares are actually very huge eruptions of UV and X-ray radiations from the sun. So these are actually high energy radiations. So when these radiations can also cause catastrophic effect. Then sometimes there can occur, like the magnetic activity in the sun can become so strong that there can occur solar storms. So during solar storms, the solar wind can also come at ultra high speeds, extremely high speeds. So these solar storms can also be very dangerous. It's like, for an example, I don't know how many of you have heard about the Carrington event. So Carrington event actually happened long back in 1859. So, like when this Carrington event is actually the strongest solar storm that has ever been recorded in our history. So when this solar storm occurred, it was so strong that even the magnetosphere and the ionosphere couldn't withstand it, and the charged particles directly hit our Earth's atmosphere. So because of that, all those electrical system, all those telegraph systems failed. Even the compasses in the compasses stopped working, because of which many ships were lost. So luckily at that particular point of time, our electrical systems and technology was not that advanced. So you just think of the condition where that sort of an event happens during our scenario. So what will happen? So all our electrical systems will fail, all the communication satellites will fail, there will be no current, no internet, no WhatsApp, no Facebook, nothing. So like you can imagine what sort of an effect it will be having on our lives today. So that is what actually the role of ionosphere in protecting our Earth from the energetic solar wind. Energetic, not only solar wind actually, solar particles I should say. Now the question is Earth the only planet in our solar system that has got an ionosphere? So do we get to see ionosphere in other planets? Actually, all it needs for a planet to form an ionosphere is, first one is it should be having an atmosphere so that there will be neutral particles to undergo ionization. And the second one is solar radiation will be reaching on it. So most of our planets except for Mercury satisfy this condition. So you can actually find ionosphere in all the planets except Mercury. Actually, not only the planets, there are plenty of satellites which has got an ionosphere and which has got an atmosphere and hence an ionosphere. So even the comets, even comets have an ionosphere. So in the solar system, all the bodies have ionosphere. But the ionosphere of all these planets differs. Like it will not be behaving in the same manner. So the behavior of the ionosphere will depend upon many factors, like what the atmospheric composition of the planet is, whether the planet has got a magnetic field or not, that is whether it is magnetized planet or not, that is an important factor. Then like what is the distance of the planet from the sun, whether it is very close to a sun or whether it is very far away from the sun. So all these factors plays a very important role in determining the nature or behavior of the ionosphere of a particular planet. So now you can ask so in case of Earth, so if the ionosphere is not there, all those catastrophic events which I mentioned earlier can happen, right? Like the communication systems can get affected. But in case of other planets and satellites, like there is no such issue. There is no one using GPS signals in there. So why we should be worried about the ionosphere of other planets and satellites in our solar system? Actually, the ionosphere plays a very crucial role in determining the fate of an atmosphere. That is, what is the atmosphere of a planet is going to be in another 100 years or in another 1,000 years will be largely influenced by the characteristics or the nature of the planet's ionosphere. So for example, I will discuss the case of Mars. So in case of Mars, the Mars is currently having a very thin atmosphere. The atmospheric pressure of Mars is only about 6 millibars. 6 millibars means it is actually 2 to 3 orders less than that of our atmospheric pressure. So you can imagine what a thin atmosphere it is. So the atmosphere is very cold and arid. So there is no liquid water or anything in Mars. But there have been plenty of studies which has shown that Mars was not so in the past. There used to be a thick atmosphere, there used to be liquid water bodies flowing on the surface of Mars and all that. So why the atmosphere of Mars is currently in this particular state? So like how the atmosphere of the Mars changed into this current situation. So that evolution of the atmosphere is largely influenced by the ionosphere of Mars. Like when people explored into what is happening with the atmosphere of Mars, they found out that these oxygen atoms are escaping from the Mars like at a very large rate. So oxygen atoms are escaping means the gas particles are escaping from the atmosphere. So that is a very like big reason for the thinning of the atmosphere. So then people started thinking like, why the oxygen atoms are escaping? Where is this oxygen atom coming from? So they further digged into it, and they came to know that this oxygen atom is basically getting produced. The basic source of this oxygen atom is within the ionosphere of Mars. So actually the atmosphere of Mars is composed of CO2, carbon dioxide. So in ionosphere, the CO2 undergo ionization and get converted to CO2 plus ion. Then the CO2 plus ion then can react with the neutral oxygen atoms, neutral, not oxygen atom, O2 gases, and get converted to oxygen atoms. So once the oxygen atom is formed, they will attain sufficient energy through various mechanisms to escape from the atmosphere. So again, the solar wind from the sun is directly impacting the Mars because the Mars doesn't have a global magnetic field like Earth. So because of that, again, the large amount of energy is getting deposited into the Mars atmosphere from those energetic particles. So in that case also, to an extent, ionosphere helps to prevent the penetration of those energetic solar wind particles deep into the Mars atmosphere. There forms a boundary called ionopause. So this ionopause forms when the charged particles in the ionosphere interact with the solar wind particles. So this ionosphere to a large extent prevents the deep penetration of the solar wind into the Martian atmosphere. But still, sometimes like it acts as a savior, but sometimes it promotes the atmospheric escape from the planet. So actually, to understand what was Mars in the previous time or what is Mars going to be in the future, you need to study the Martian ionosphere. So not only with Mars, this is the case with actually every planet. If you look into Venus or Jupiter or Saturn, anything, like ionosphere is playing a very prominent role in determining the fate of the planet's atmosphere. So again, the question can come: why we should be worried about the atmosphere of other planets? We are happily living on Earth, then so we should be concerned only about the Earth's atmosphere. So why we are worried about other planets' atmosphere? Actually, like in planetary science, we study about any planet or any satellite with the main intention of having a better understanding of our own planet Earth. So we want to know in future what is going to be the fate of Earth's atmosphere, whether it is going to be a future Mars where the atmosphere is very thin and cold and in a arid condition, or whether it is going to be a future Venus where the atmosphere is hot like hell and is fully composed of carbon dioxide. So we need to know like how our atmosphere will be evolving in the future. So to get to know about that particular aspect, you actually need to study about how the ionosphere and the plasma environment of terrestrial planet, especially the Mars and Venus, will look like, or is looking like, and it's going to look like in the future. So that is the main intention of studying the planetary ionosphere. And also, if you like, I was talking mainly about Venus and Mars. If you look into the outer solar system, like Jupiter, Saturn, and Uranus, etc., so all those planets have very tremendous magnetic field. So there, the picture itself is totally different. So in case of Venus and Mars, they don't have a magnetic field at all. So there, the sort of processes that are in action is different. Whereas in case of the outer solar system planets, the magnetic field is entirely strong, is extremely strong, and you have a very thick ionosphere over there. So the mechanisms operating there is completely different. So, but the thing is that we say the atmosphere of Jupiter or the outer solar system planets are very pristine. That means since the formation of this planet, there have not occurred much changes in in the atmospheres of this particular planets as compared to the atmospheres of inner solar system planets. So if you want to know how our atmosphere was in the past or at the time of solar system formation, we actually study about the ionospheres and the plasma environment and the atmospheres of outer solar system planet. So this is what ionospheric study is all about. So now, what is this aeronomy which I mentioned about in the title? So this must probably be the first time that you are hearing about this word aeronomy. So aeronomy is nothing but whatever I have talked so far. That it is that branch of space physics which explores the structure, dynamics, and the energetics of the planetary upper atmospheres and ionospheres and its interaction with the sun. So in aeronomy, we dive deeper into how the neutral atmosphere is behaving, how the ionosphere is responding, how the changes in the sun is affecting our ionosphere and upper atmosphere, and all that. So, but when I say this, you should keep one thing in mind. None of these branches are like independent things. That is, heliophysics is one branch, or space weather is another branch, and aeronomy is another branch. It is it is not at all like that. These all are interconnected. So, if someone wants to learn a topic of aeronomy, they should definitely be studying about the sun. They should definitely be aware about space weather events. So all these are interconnected. So like this aeronomy is that branch which actually studies how the entire plasma environment of the solar system is working, how it is formed, what is its structure, what is its dynamics, and how it is going to evolve in the future. So if you talk in terms of research aspect, there I would say in aeronomy there are basically three main branches that people work on. So one is the instrumentation, the second one is data analysis, and the third one is the modeling and simulation. So I would like to elaborate each of this a bit more. So instrumentation stands for, like, we always send missions to planets, isn't it? So you all might have read about all of the India's latest mission, like Chandrayaan 3 or our Mongolian mission and all that. So that designing that mission itself is actually a career. Designing a mission, planning a mission, then the execution of the mission, everything is a study of, or like is a part of space physics. Then again, instrumentation. That is, all the spacecraft will be having instruments instruments or payloads, we call it generally, for payloads for measuring this features, aeronautical features. So developing that instrumentation, like instruments, as an example, I could say, like already I mentioned during my presentation, like magnetometers, then there can be spectrographs, there will be Langmuir probes for measuring the electron density, mass spectrometers, etc., etc. So developing all those instruments is what comes under the instrumentation section. Now the second branch is the data analysis. So data analysis means you get observations from these instruments, right? Like for example, the magnetometer on board Aditya measures the magnetic field, but what it measures, like the data that is coming from this magnetometers are actually some numbers. So you need to analyze it, you need to understand it, like what these numbers are telling you about the magnetic field of the sun. So that is what comes under the data analysis section. Then another part is modeling and simulation. So that is one thing which I mainly got trained in, even though I currently work in data analysis as well. So in modeling and simulation, like what we do is we actually simulate the ionospheres. We develop programs, we develop codes, and we simulate what is happening over the ionosphere to get a feel of how the processes are actually happening there. To get a physical feeling of what is happening over here. Like these sort of instruments you cannot execute in lab, isn't it? So these are actually very these are processes that are actually taking place in very large environment. So you just can't recreate it in a small confined space in a lab. So that's why we basically depend upon the modeling and simulations. And modeling and simulations, like these are important while designing a mission as well. Because if you want to design an instrument for measuring a particular aspect of the ionosphere, say you want to measure the electron density of the ionosphere using a Langmuir probe, but for designing that Langmuir probe, first you need to know what is the expected level of electron density in the ionosphere to which you are sending the instrument. So for getting that particular aspect, you need to do modeling and simulation. So these are three areas in which you guys can explore into if you are looking forward for a career in space physics. So again, career in space physics is not just confined to those three. So as I have written over here, that can include working on a new satellite or developing a technology to map a satellite, map a planet or a satellite. Then you can have your own discoveries of new satellites in our solar system, say like an undiscovered satellite of the Saturn, which was not known so far. So that sort of discoveries using telescopes, everything comes under this branch of space physics. So a career in space industry could include any of these areas and much more. So I hope I'm really looking forward to see many of these young phases, as I said in the beginning, in the space physics career very soon, maybe within another 5 years or so. So all the very best for that, and keep exploring. And with that statement, I conclude my presentation, and thank you.
Hello, ma'am.
Yeah.
Am I audible?
Yes, yes, I can hear you.
Ma'am, shall we conduct a question answer session so that can people can ask questions?
Sure, sure.
Is there time for it?
Sure, sure, we can.
Thank you, ma'am. So next is a question answer section. So everybody can ask their questions. Can put in a comment box or can unmute the mic and ask the question. Is there anyone?
I can see someone raising the hand. Yeah, please proceed to ask.
Yes, ma'am.
Aditya.
Hello, ma'am. Am I audible?
Yeah, yes, yes.
Ma'am, you told about that Lagrangian points, right?
Yeah.
That when a satellite is placed between two planets, they will experience that gravitational force and all. So, if we consider the Earth L1 mission and it's placed between the Sun and the Earth, so won't that satellite be affected by the other planets like Mercury and Venus? What about their gravitational force effect on that satellite?
No, actually, you might have noticed when I said Lagrangian point, it is actually a point very close to Earth. It is just 1.5 million kilometers from Earth. So I should, okay, I have closed my presentation. Okay, I will explain. So it's actually a point which is close to Earth. So the force, the gravitational attraction force, which the spacecraft experience at that particular point will be most prominent from Earth and the Sun. Actually, the gravitational pull of the Sun will be the most dominating effect. But since it is close to Earth, there comes the gravitational effect of Earth as well. So when compared to definitely the spacecraft will experience the gravitational pull from other planets as well, like as you said, Venus and Mercury and all that. But still, when compared to the force the spacecraft experiences from the side of Earth, it would be much greater. That is, the pull from the Earth would be much greater as compared to other planets. So we don't take much them into account.
Yes, ma'am. Okay, thank you.
Yeah.
Ma'am, one more question.
Yeah.
Ma'am, you said about that in the upper layers of the ionosphere, there are only small number of electrons, ions. That's why there is a large amount of temperature produced.
Not ions. Not ions. Actually, I was talking about neutrals. This temperature actually. Am I audible?
Yes, ma'am.
Not ions, like you said, like the large temperature of ions. So it is not the temperature of ions which I talked about. In the upper atmosphere, like when we talk about the temperature of atmosphere, we are actually referring to the temperature of the neutral particles in the atmosphere, not of the charged particles. So in the upper atmosphere, the neutral particles are very less. That is what we mean when we say the atmospheric pressure is very less over there, or the atmosphere has got a very thin nature. That means the neutral particles are less, not the ions. You were asking, you were about to ask something.
Yes, so if there are, you said that if there are low number of neutral particles, there will be a higher amount of temperature produced because each neutral particle will be able to gain large amount of energy.
Exactly.
So if there are, suppose there are a large number of neutral particles over there, then won't the collective temperature will still be the same if they gain the equal number of energy?
No, first of all, a large number of particles can't stay there. Basically, because we have Earth underlying there. No, Earth pulls everything towards it because of the gravity. So that is one of the basic reasons why you have a large number of particles near the ground level. So so that is why you basically have lesser number of particles in the top side and large number of particles at the bottom region. Now, suppose as you said, you happen to have a large number of particles in the top side itself, then the temperature will not be as high as what we see right now, because the energy will be distributed among this larger number of particles, and which will bring down the air temperature to lower values.
Okay, ma'am.
Yeah. Okay, somebody has put a question in the comment box. How is space-time bent by mass and what causes gravity? Can gravitons be really real? I'm very sorry to say that I'm not an expert in this field. So mostly someone who is an expert in the field of relativity might be able to answer this question. So this is not something which actually comes in my area of work. I'm sorry for that. So anything else? Yes, Deepak.
Ma'am, what advice would you give to students who are considering pursuing graduate studies or careers in this field based on your experience and journey in this field?
Okay, Deepak. Actually, I don't know what to tell you because as far as Deepak, you are a BTech student. Am I right?
Yes.
Okay. So I am actually someone from a science background. I did my master's in physics and then I turned to PhD. So as a career advice, what I would say is that if you are really interested in pursuing space physics as a career, you can definitely go for a PhD in space physics. But first of all, since you are BTech, you need to do your post graduation to get into a PhD. So once you get into your PhD, like then the choice is yours, like in which stream which you want to turn into. So since you are going to be an engineer very soon, I would suggest like instrumentation would be your best part because our country is now in large demand of engineers who are working in the area of space physics because we are going to have like mission to Mars. Our like ISRO has recently declared the mission to Venus as well. Then there will be plenty of missions happening to moon as well. So ISRO is like planning for plenty of missions to space, which will be happening in like within some 2050 or so. So what I would advise you is like go for your masters and then do a PhD. And while standing within your PhD, you will be able to have a more clear picture of what you are actually interested in, whether it is instrumentation or it is modeling or anything.
Thank you, ma'am.
Yeah.
Hello, ma'am.
Yeah, someone has asked me, can you say how to become an astronomer? Interesting. Okay, astronomer. Like, actually, you don't have to learn anything professionally to become an astronomer. I don't know how many of you know actually. There is actually group or WhatsApp group or Facebook group, something like that. This is a group of amateur astronomers. So they usually meet up here in Trivandrum itself. They plan for this sky, like late night sky observation and all that. So all those amateurish things are happening. Like you don't have to get into any course or anything if you really want to be an astronomer. There are plenty of non-professional astronomers in Kerala. So maybe you can explore in that particular aspect. So if you are really, if you really professionally want to get into astronomy, again, what I told to Deepak, I will repeat it here. Go for a higher degree in space physics or astronomy. So like you have foreign universities as well. Apart from India, you have foreign universities as well, which offers you plenty of courses in space physics and astronomy. Like in foreign universities, even astronomy is taught as a main subject in the like graduate courses as well. Like not only for your PhD and all, from your graduate classes onwards, you have the opportunity to learn space physics. I mean astronomy. Again, you have plenty of online courses available and all that. So nowadays, you have a like number of opportunities to get into the field of astronomy and to be a professional astronomer. Yeah, like someone has put on the comment box that Astro Kerala Breakthrough Science Society. That is what I actually meant. I meant Breakthrough Science Society. So maybe you can explore further into that, Abhishek. Yeah, Aditya has raised hand.
Yeah, hi. Am I audible?
Yes, yes.
Yeah, okay. First of all, really great class. I loved it.
No, thank you.
Yeah, and I want to thank Sahal for inviting me. And so I have a question from a talk about gravitational waves I attended last week. It was a different talk, and I wanted to ask the speaker this question, but I could not. So I hope if you could help me with it. Right. So, could you explain the concept of multi-messenger astronomy and how it relates to gravitational wave observations?
So I'm sorry to say that like gravitational waves is again something completely out of my regime. So I don't think I am the person to comment on it.
Right. Yeah. Thank you so much.
Yeah. So anything else?
I do have one more question.
Sorry.
I do have one more question.
Yeah.
Yeah. So it's regarding black body radiation. Is that cool?
Again, actually, this black body radiation, all those things actually comes as a part of astrophysics rather than that of space physics. As I said before, like in space physics, we are more or less constrained, contained within our solar system itself. So, like this black hole and all that. Actually, you were mentioning black hole, isn't it?
Black body radiation.
Black body. Oh, sorry.
But it was gonna get connected to that. I was gonna ask the difference between.
In my head as black hole. Okay, please ask.
Yeah, but actually it goes to a black hole actually. So the point is, is there like a way to distinguish between a typical black body radiation graph and a Hawking radiation graph?
Actually, I would say the best way to distinguish is that a typical black body radiation graph you will see only in textbooks. So if you actually measure the radiation spectrum of a body, it will never be a paka black body spectrum. You will get to see a large amount of angulations and all that. So I don't actually understand when you say how do you distinguish, because you really get, like, if you look into the black body spectrum of this what you call sun itself, it is not a perfect thing. It's not a perfect black body curve. You get to see a lot of angulations and all that. And again, Earth also has got a black body spectrum, which is again not a perfect one. You will get to see deviations from the perfect black body behavior. So when we say the black body spectrum and all that, it is actually an approximation. We say approximately this behaves like say black body.
Right.
Yeah.
Yeah. Okay. Thank you.
Okay, so any other questions? I guess no any other questions. So let's move on to the last section. So I invite Pranav, the Secretary of SETS, for giving the vote of thanks.
Hello everyone, am I audible?
Yeah.
So good evening everyone. So from all of your wonderful questions, it's evident that you have enjoyed this session today. So I'm thanking on behalf of SETS Prasad to Vrinda ma'am for taking her time to share her expertise and experiences us with today. Vrinda ma'am's extensive knowledge and passion for space physics has truly enriched our understanding of the cosmos and the exciting opportunities it holds us for the exploration and development. Her journey from Space Physics Laboratory at VSSE to her current role as Inspire faculty at NCESS is not only inspiring, but a testament to the boundless possibilities that awaited those who dare to dream and pursue their passions relentlessly. Now, today's talk has not only been educational, but also a source of motivation for all of us here. It has reminded us the importance of curiosity, perseverance, and collaboration in the pursuit of scientific knowledge and exploration beyond our planet's boundaries. Now, as we reflect on ma'am's words, let us consider the invaluable opportunities that wait us for joining SETS. Now, SETS is an organization that provides a platform for students like us to engage on hands-on projects, competitions, workshops, and networking opportunities that can shape our futures in the field of space exploration. So all of you who are interested in signing up for SETS, I urge you to seize this opportunity to be part of a community that is dedicated to pushing the boundaries of human knowledge and exploration. Today, we can inspire each other, learn from one another, and contribute to the incredible journey of humanity's exploration and development of space. Now, once again, ma'am, we thank you so much for your enlightening talk, and we thank all of you today for joining us. Now, let's continue to reach the stars as we embark on this exciting journey. Thank you, guys.
So thank you, Pranav. Thanks a lot.
You're welcome.
Yeah.
So that's a wrap. See you soon at the next event. Thank you and have a nice day.